Hello and welcome to our series of understanding the Rust programming language. In today's video, we will understand ownership and borrowing in Rust. Many programming languages don't require you to think about the stack and the heap very often. But in a systems programming language like Rust, whether a value is on the stack or the heap affects how the language behaves and why you have to make certain decisions. Parts of ownership will be described in relation to the stack and the heap later in this chapter, so here is a brief explanation in preparation. Both the stack and the heap are parts of memory available to your code to use at runtime, but they are structured in different ways. The stack stores values in the order it gets them and removes the values in the opposite order. This is referred to as last in, first out. Think of a stack of plates. When you add more plates, you put them on top of the pile, and when you need a plate, you take one off the top. Adding or removing plates from the middle or bottom wouldn't work as well. Adding data is called pushing onto the stack, and removing data is called popping off the stack. All data stored on the stack must have a known, fixed size. Data with an unknown size at compile time or a size that might change must be stored on the heap instead. The heap is less organized. When you put data on the heap, you request a certain amount of space. The memory allocator finds an empty spot in the heap that is big enough, marks it as being in use, and returns a pointer, which is the address of that location. This process is called allocating on the heap and is sometimes abbreviated as just allocating. Pushing values onto the stack is not considered allocating. Because the pointer to the heap is a known, fixed size, you can store the pointer on the stack, but when you want the actual data, you must follow the pointer. Think of being seated at a restaurant. When you enter, you state the number of people in your group, and the host finds an empty table that fits everyone and leads you there. If someone in your group comes late, they can ask where you've been seated to find you. Pushing to the stack is faster than allocating on the heap because the allocator never has to search for a place to store new data. That location is always at the top of the stack. Comparatively, allocating space on the heap requires more work because the allocator must first find a big enough space to hold the data, and then perform bookkeeping to prepare for the next allocation. Accessing data in the heap is slower than accessing data on the stack because you have to follow a pointer to get there. Contemporary processors are faster if they jump around less in memory. Continuing the analogy, consider a server at a restaurant taking orders from many tables. It's most efficient to get all the orders at one table before moving on to the next table. Taking an order from table A, then an order from table B, then one from A again, and then one from B again would be a much slower process. By the same token, a processor can do its job better if it works on data that's close to other data, as it is on the stack, rather than farther away, as it can be on the heap. When your code calls a function, the values passed into the function, including, potentially, pointers to data on the heap, and the function's local variables get pushed onto the stack. When the function is over, those values get popped off the stack. Keeping track of what parts of code are using what data on the heap, minimizing the amount of duplicate data on the heap, and cleaning up unused data on the heap so you don't run out of space are all problems that ownership addresses. Once you understand ownership, you won't need to think about the stack and the heap very often. But knowing that the main purpose of ownership is to manage heap data can help explain why it works the way it does. Let's take a look at the ownership rules. First, each value in Rust has an owner. Second, there can only be one owner at a time. Third, when the owner goes out of scope, the value will be dropped. Let's learn how stack memory works. We will pass variables into one another and see if anything works properly or not. We can see, in case of stack variables, we have no issues while passing variables around. This is because stack copies the data in case of each variable. And these variables has no relation with one another other than they are on stack. Let's try the same approach with heap-based variables. We will find that this can cause errors. As soon as we use some string after passing ownership to some other string, we can see a bunch of errors. To fix this, we can clone entire heap-based variable and put a new clone on heap. Now these variables have no relation other than the fact that both of them are on heap. This solves our problem, but is costly. Let's see a new approach of borrowing. Let's borrow our sum string variable into a new variable and we will see that we don't get the same error as before. Let's build and run our project using cargo run. We will see that everything works as expected. Let's make sure we are borrowing some string variable and not cloning. For this we will mutate our sum string variable using a function. Everything works as expected. Let's create a scenario where we do not create a new variable but pass our variable string as mutable borrow. Everything works as expected. That's it for today. If you haven't already, don't forget to like, share and subscribe. Thank you and visit again. Happy coding!